Okay, well, let's go ahead and get started. This is our second webinar of today. We have one more after this. Today, we're going to be covering a little bit more technical in-depth of OpenShift and Linbit Sds and how we integrate into OpenShift. We've got Moritz, who is our Kubernetes/OpenShift expert here at Linbit. And we have Taylor Smith, who's the partner manager and from Red Hat, and she helps us at Linbit make sure our stuff works with Red Hat OpenShift.
Super. So I'm just going to give a very brief overview of OpenShift to lead into Moritz's presentation and demo. So my name's Taylor. I work as an engineering partner manager at Red Hat within the partner ecosystem organization here. So my team and I work directly with partner companies in order to help facilitate and manage their product integration on our platforms. So OpenShift is a trusted Kubernetes enterprise platform. It's security-focused, consistent foundation that enables modern hybrid cloud app development and lifecycle management for any app in any environment. OpenShift is self-managed, and it includes the Red Hat Linux operating system, container runtime, networking, monitoring, container registry, authentication, and authorization solutions. So these platform components are tested together to ensure a unified experience on whatever cloud provider or on-prem device you're deploying on. So with this foundation of a trusted enterprise Kubernetes platform, we then add enhancements to deliver an app platform with all the components you need that are fully integrated and supported in order to help you build, deploy, and manage the containerized applications. So at Red Hat, across the product portfolio, we use an open source development model to deliver enterprise level products. So the value is our ability to turn a wide variety of open source projects into production ready, stable, and secure products that we support. So when the upstream community declares a release is ready, we then take those upstream releases and typically end up finding a bunch of defects that we then fix in corresponding downstream releases. We do this because we've been contributing to Kubernetes as well as many other open source projects that OpenShift is based on since the beginning. And Red Hat is actually the largest enterprise developer of Kubernetes next to Google, which is the project sponsor. Kubernetes is the open source de facto standard for container orchestration, and OpenShift is the leading enterprise Kubernetes platform. So quickly, what is the same and what sets OpenShift apart from vanilla Kubernetes clusters? So OpenShift is based on Kubernetes APIs and is fully compatible with the kubectl command line tool. The OpenShift specific command line tool, or OC, complements kubectl as well as adds some additional helpers. If you have containers running on Kubernetes or another Kubernetes-based platform, you don't have to do anything special to make your container compatible with OpenShift. OpenShift is Kubernetes, but it adds additional platform-level management features for enterprise use cases. So these cluster management tools like monitoring, security mechanisms, network management, it all comes out of the box with your OpenShift subscription. And it's also important to note and reemphasize that Red Hat is connected and deeply committed to the Kubernetes community upstream. We're the second leading contributor behind Google, as I said, and we were one of the first companies to work with Google on the project. Rel Core Os is the foundation for the OpenShift platform. Core OS shares the same kernel as Rel, Red Hat Enterprise Linux, and is optimized for running containers and managing Kubernetes clusters at scale. We also have a rich ecosystem of products from our software partners within OpenShift's embedded operator hub. And then lastly, OpenShift supports hybrid cloud, multi-cloud, and edge footprints with your OpenShift subscription. And lastly, just to highlight some quick key benefits of OpenShift that I wanted to call out. OpenShift is security focused and delivers security for the entire platform stack. OpenShift has a wide variety of certified secure container content and services from our vast partner ecosystem, including Linbit. The platform offers streamlined install and upgrades, even in air-gapped and disconnected environments. OpenShift offers the benefit of app portability as well, with lower overall operational costs across cloud environments and edge footprints. And then lastly, operators operators are a big benefit of OpenShift, obviously. So the automated install and day 2 operations are key features of OpenShift that make it easier to administrate and upgrade. Operators, which is a core element of our architecture and something we like to talk about a lot, provide the foundation to make this happen. And this is not by any means a comprehensive list, but I felt that these were some of the most important to call out. And with that, I will stop sharing and shift it over to the more exciting stuff.
Thank you, Taylor. I'll just quickly share my screen. And we can hopefully resume where we left off. Hi, my name is Moritz. I'm working here at Linbit and working mainly on integrating Linbit Sds with Kubernetes and OpenShift and also some other platforms. So before we get to the actual technical part, I just want to give you a quick overview over Linbit Sds. What was that again? So Linbit Sds is a modular storage solution that can integrate with many different platforms. So in this case, I want to highlight, of course, OpenShift and Kubernetes, but we also support other platforms, at least every platform that is running on Linux, although I have to say there's maybe in the future a bit better support for Windows coming up, but that's not for me really to talk about. So as I said, it's mainly a Linux storage solution, which is built from open source components, mainly developed by Linbit, but they are all freely available. We pride ourselves with having a very fast and low overhead storage solution that still delivers high availability and reliability without having any specialized hardware requirements or dedicated storage nodes or so on. And as a secondary benefit of that, we have very low resource requirements, which make Linbit Sds also suitable for running on edge devices, which perhaps don't even have local storage, but you can have dedicated storage on different nodes. So this modular package is really a stack at the core, at the heart of every Linbit SDS for every platform. There is DRBD, our replication tool, let's say, which is actually a Linux kernel module, which enables us to deliver or enables us to get to replicate volumes with very low overhead over the network, and our storage management software Linstor, with which you can configure a whole cluster of nodes and their storage devices and set up DRBD replication between them and so on. And on top of this core, we have the flexible set of integrations. And for OpenShift, these integrations comes in the form of a CSI driver. CSI stands for Container Storage Interface, which is the de facto standard for integrating any storage solutions with Kubernetes or OpenShift. We have an operator which makes it very easy to install, because oftentimes if you have a very modular software, there's lots of bits and pieces you need to worry about. But with the operator, this is all unified into basically one single interface, and you don't have to worry about too much about the installation. And then lastly, the high availability controller is a special controller for OpenShift, where oftentimes you'll have storage attached to a pod or a workload, and in Kubernetes or OpenShift, this is sometimes failures happen, and normally you would just expect the cluster to self-manage that failure. But if there is storage involved, then this can be a little bit slow in OpenShift. And so we have a special component that speeds that process up as long as you're using Linbit Sds. To get into a bit more detail, we have at the lowest layer, we have DRVD. As I said, it's a Linux kernel module, and you can think of that as basically RAID 1 over the network. So you have, for example, 2 nodes, and you open a DRVD device on one, then everything you write on that one device is also written to a secondary device, as long as you have that replication configured. But that's the kind of the most basic case that DRVD covers, but you can also do lots of different other configurations. For example, you could have your DRVD device on a node which doesn't even have any local storage, and it just connects over the network to 2 other nodes, 3 other nodes, 4 other nodes, and reads and writes data from those nodes, and those nodes also replicate internally if that's required. And so you have your data replicated across many different nodes, and if one node fails, then you can still have the data still available on the other nodes. So that's the core of both our high availability claims and also the core of our low overhead and replication speed claims. Because this is built into the Linux kernel as a kernel module, you have a very low overhead. You don't have to go through any user space daemons to write to disk. Then on top of that, as I said, there is Linstor, which is actually Linstor itself has 2 different components. There's the satellites, which are worker agents, and these satellites are coordinated by a single controller. And that controller in turn has an API, which can be either used to control it via a command line client or a web console, or as you will see, the integrations we have for OpenShift. And Linstor does all the hard work for setting up storage. So uses local storage devices on a node, pulls them together, slices off different volumes in whatever size you requested, sets up DRVD replication between all those nodes, and so on. And this is also very flexible because you have lots of control with the API. You can adapt it to many different requirements. You can run it native. You can run it somewhere in the cloud. You can run the Linstor satellites on edge devices and use that to connect DRVD volumes without local storage to some replicas that do have storage. So then now for the OpenShift specific part, we have the CSI driver, as I said, that connects Linstor and OpenShift. And we try really hard to follow the latest updates to the spec, and also to have as many features that Linstor supports exposed through native resources in OpenShift. So what that means is you can have optimized volume placement. So if you start a workload on a node, then you can expect in the normal case that if there is local storage available, then Linstor will also use that local storage for this workload. We support volume cloning, so you have your initial set of you have your initial volume and you maybe want to experiment with the data that was written to that volume a bit. And then you can do volume cloning. You can create snapshots, and more than just snapshots, you can even back up these snapshots to some object storage like Amazon S3 or somewhere offsite. And for example, if you're using OpenShift with QBWord, which is a kind of plugin for OpenShift that supports running virtual machines using OpenShift, then you can even do live migrations of virtual machines as long as they are running on Linstor volumes. And as I already started, or as I already tried to introduce at start, there's also the Linstor Operator, and which is really a quite nice way to deploy software on OpenShift. We use the Linstor Operator to package our solution and automate the setup and day 2 operations. So for example, if you're adding nodes or removing nodes from your OpenShift cluster, the operator will also scale the Linstor cluster. If you have any topology information, so your cluster spans multiple zones or even multiple regions, then this information is also synced with Linstor, and Linstor can do some smart scheduling based on that. It sets up monitoring, which is one of the benefits of the OpenShift Kubernetes distribution. It already comes with a monitoring stack pre-configured, and we can integrate with that as long as you have user workload monitoring enabled. And it helps with other upgrades and day 2 operations. And with that, I want to move to the actual exciting part, at least for me, seeing it in action. And to start with, I already have an OpenShift cluster up and running here, and currently browsing the web interface for that. And as you can see, it has 6 nodes. 3 of those are control plane nodes and 3 of those are worker nodes. And we want to deploy Linbit Sds there and set up storage and want to actually use it to run some database applications. So to start with, I've also got that configured on the command line because that's one step you need to command line for. A lot of the later steps we can also do via the web interface, but we'll be using Helm to deploy our operator, and that's just easier to do on the command line. So to start with, let's create a new project for our storage solution. And let's make sure that I have added the Linstor repo. And then one last thing, I need to create a pull secret for our registry, which we use to distribute Linbit SDS. If you're a customer of us, there's also open source image available at the open source version of the operator. But let's start with that. We have the secret created. And now I would just need to write Helm install that, but I want to do some customization first, and that I can show you here. So because our Helm chart is also working on Kubernetes, on vanilla Kubernetes, we have to do some changes to get it to work with OpenShift. So normally we set a security context, but OpenShift already automatically sets that on a per project basis, so we don't have to do that. And if we wouldn't disable that, then that would conflict with what OpenShift tries to enforce. And next thing is we want to disable the legacy etcd deployment. Previously, we needed etcd as a database for Linstor, but nowadays you can use the Kubernetes API directly as a data store for Linstor. So this is what these lines do. And then, as I said, DRBD is a kernel module, and so you need to load the DRBD kernel module some way, and we deliver that using an injector image, which comes with the right kernel modules prepackaged and installs them. And the last thing here is you can also automatically set up SSL or TLS between the different components, so all the communication between the components is encrypted. This is what we will do here. And so let's do that. I have also overwritten some affinity settings so that it actually deploys on all the nodes, but that isn't too interesting. And actually, one thing I'll show you later quickly. I've also already prepared the configuration of some storage pools so that Linstor knows where it can create volumes on each node. So now the installation starts. Helm will create all the required deployments. And if I've configured everything, then first the operator will start, and then the operator will deploy the rest of the stack. So I've promised you a quick look in the storage pool configurations, where we just say that we want to configure an LVM thin storage pool. So we want to thin reprovision our logical volumes on nodes. And this is an empty device that is available on all the cluster nodes, which I added beforehand. And the operator will ensure that the storage pool is configured and available. So let's see where we're standing currently, or actually let's switch over to the web interface. As you can see, there's lots of different components currently starting up. We have the operator originally. Now there's the controller starting up, which I have configured to use 2 replicas so that if one node fails, then the other one can take over. And CSI containers, which integrate with the controller, and our satellite nodes are already up and running, which hopefully means we'll be able to start very soon. Let's see. Currently, controller is starting up, and now it has started up. And quickly take a look at where it's currently standing. So it's currently.
I was going to say, we do have a couple questions if you want to answer those while we wait.
Yeah, sure.
So one question was, how many pods can actively write to the volume? So
that it depends on how many pods you can run on one single node. So we are only supporting the read. What's it? Read write. Single read write. So only one node at a time can write, but there's since I think Kubernetes version 120 or something like that, it's possible to mount the same volume on the same node in different pods. So you can't share the volume at the same time over the network, but you can do it as long as your applications are running on a single node.
Okay, and the follow-up question was, can we integrate the storage with Prometheus in order to receive metrics from it?
Yes, we can do that, but as actually should be set up. Okay, I think there's something stuck in here because right about now it should be done. Don't know why this happens sometimes, but let's just quickly force the operator to restart, and then it should register the nodes correctly. Actually, for Prometheus, I can show you, where is it? Is it on the targets? If I set everything up correctly, then there should be storage resource. But anyways, so yeah, the Linstor satellites or DRBD, we have a Prometheus exporter, and for Linstor itself also has a Prometheus endpoint which you can scrape. And normally the operator would set that up, but I think I've disabled user storage, user monitoring in this cluster. Normally it would create the right targets right here in OpenShift, because it detects that the Prometheus operator is already running. So let's jump back in here and see if there's some progress here. Okay, now there's some progress. And if I configured everything correctly, we should also have a storage pool available here. Okay, so that works. And now I want to also show you that our graphical interface, which I can expose using a root here. And let's select the Linstor service and let's secure that root. And because I haven't set up a proper certificate for this cluster yet, not available, but that should be available relatively soon. And so right now we have 7 nodes, no resources, no volumes, and here you can browse all that same information that you have in the storage using the command line client. You can also have that available here. And the storage pools, you can see how much free space there is on each node, and so on. So now everything is basically set up. From the Linstor side, everything is ready, but there's still some things you need to do on the OpenShift side to get storage working. First of all, you need to create a storage class. Let's just call it storage class Linstor 3 replicas. And let's use the delete policy, volume binding mode. And here you have to select the Linstor provisioner. And then I'm gonna say I want to auto place it on 3 different nodes. So Linstor will create for every new volume you create, it will create 3 replicas. And let's create the storage class. And actually, one other thing I need to do is this one is currently the default storage class, and I don't want that. So I'll just remove that and use our newly created storage class and mark it as the default. Why am I doing this? Because I actually want to show one of the nice things about OpenShift is that it comes with a lot of nice features for developers. And let's say I want to start a new database and just create one from a template. Let's use the Postgres database and just need to initiate this template. Maybe I want to create a 5 GB volume for this database. And then we'll just wait until that is created. Perhaps I shouldn't have added it in the storage pool, but it's fine. And it's already created here. And this one has a persistent volume claim for whatever data it wants to store. And this is, as you can see, it's created with our storage class. That's because I changed the default storage class, and is already backed by a persistent volume. And if I look now on the Linstor side, on the Linstor UI, I can already see, first of all, this is the resource that was just created, and there's a resource group, resource group is basically the same as a storage class in Linstor, and already deployed all 3 replicas, and one of them is currently in use because that's where our pod is mounting that volume. And I think this pod should already be running. Yes, and if I take a look here, then the data directory is backed by this DRPD device, and that replicates across all the different nodes. So even if now Linstor fails, for example, or crashes, DRPD would still replicate the data in the background. And so now you can see that is running on, let's say, what node was it running on? On this node, but maybe that node has some issues. So I'll quickly mark this node as unschedulable. And if I now go back and delete that pod, the pod will be, or there will be a new pod on a different node, which will still use the same volume and should still access the same data. So now it's on a different node and takes a bit of time before all the volumes are attached, but now it's running and it's using the same device in the background. Still this DRPD device, but now on another node. So there's that. What you can also do, and now I'm switching back to the administrative view, is you can create snapshots. And for snapshots, you need a snapshot class. Let's quickly create one here. And here I need to change the driver to whatever the storage class driver was previously, and that one here. And with that, I can now create a snapshot of this volume right here. Let's just create it, and now it's already ready. And if I look at Linstor view, where was that again? Maybe I'll just quickly show it on the command line. So now there's a snapshot in Linstor, and this snapshot currently is only exists on the cluster. So there's no, if you would lose your cluster for whatever reason, then that snapshot is also lost because it's not backed up to some offsite location. And for that, we have some other, you need a different snapshot class. Let's call it Linstor backup class. And here we need to change it to Linstor.com. And we currently support backups with any S3 compatible storage. And now I just need to quickly find the right parameters for that, so that I can actually demonstrate that. So like a storage class can have parameters, a snapshot class can also have parameters. And here we instruct the CSI driver that this should be backed up to S3, and you can specify your bucket, your whatever endpoint you're using. And of course, you want to secure your bucket. So there's a secret you can reference that that you can use to that you can reference, and then it will use that whatever is in that secret as the access to your snapshot or to your bucket. So we have created that, and I quickly need to apply that secret because I haven't created it quite yet. So let me quickly apply that secret, otherwise this demonstration won't work. And let's go back to our persistent volume claims, and I want to create another snapshot, but this time I want to use backup, and let's call it backup. And this will also take just a little time, hopefully. Yep, so now it's ready. And first of all, there's also a local snapshot created. But there's also a backup created, and you can see it was shipped successfully, and I can hopefully show you this here. Yeah, so it's now available in your S3, or maybe you have some MinIO or some other form of compatible object storage available. And yeah, you can also then restore from those backups. Quickly, maybe we will use this one, and you can select restore to new persistent volume, and maybe you want to have it as read-only. Restore, and oh, no, wait, that was a bad idea. I need to I need to, or no, actually, let's do it like this. We restore it. And then we need some, before the persistent volume is created, you need some consumer pod because we've specified that in our storage class. So I'll quickly create that one here. Volumes. And I've already forgotten what I named this persistent volume. So let's see. That one, and let's mount it somewhere. And create that. And now this persistent volume is created, and this container is creating and should be running very soon. And apparently I've made a mistake because I probably shouldn't have specified, shouldn't have overwritten the whole www directory. Yep, it was probably a mistake. So let's try that again. So you can see that this is all live, nothing pre-planned. No. Let's try that again. Hopefully it doesn't crash this time.
So we do have some questions that popped up. One is there a minimum latency requirement among worker nodes where Linstor volumes are placed in order to have synchronous replication?
There isn't really a hard limit. There, at some point, it might not be that pleasant to work with, I would say. I'm actually not a DRBD expert. Maybe someone is here to answer that better than me. But normally, all the if you're running in any public cloud or so, which have dark fiber between their compute centers, then that is more than good enough to support synchronous replication in DRBD. Maybe not if you're doing it from across the planet, but certainly if you're within the same region or maybe the same kind of area on the world.
Okay. So another question in that same line while you're checking that out is, I know that DRBD can asynchronously replicate to a DR site. Can we replicate Linstor to another OpenShift cluster?
Not directly or not integrated currently. What you can do is using this snapshot backup creation feature and have a common set of snapshots or common snapshot location basically for your snapshots and use that. Otherwise, Linstor itself isn't really currently capable of, or there is there's another possibility to this currently to the backup shipping that I showed, the S3 shipping. You can also ship snapshots directly to other Linstor clusters. You just need to expose the controllers in some way so that they can reach each other. And also the nodes, I think, need to be able to communicate in some form so that you can set up. That is, I guess you could say this is an asynchronous replication as long as you're fine with maybe not having always having the latest, most up-to-date data. As long as you're shipping snapshots every hour or so, that should be fine. So yeah, because this now finished up and I actually was just wrapping up my presentation anyway. This is the user data that we restored from the snapshot, which is currently not accessible in this pod because this is running on a different, it is using a different volume ID. Okay. With that, I want to quickly hop back to the presentation and to tell you that I want to show you where you can find more information on Linbit SDS and also OpenShift. And I guess we already kind of started with the Q&A, but if there are any more questions, share them now.
Let's see. There was another one from Daniel. Can node-specific paths be specified in storage pool config? For example, can we configure differently named devices on different nodes in the storage pool? And can they be used by ID paths?
That is possible, but it's currently not automated. So what I showed you initially with the storage pools configuration, this was kind of what we did with, or what we have for the operator, which is the quick start version which you can use in most scenarios where you have always the same node or the same type of node everywhere, but maybe you have some nodes that have storage and some don't have storage. And then you can either have multiple satellite sets, which is the resource our operator operates on, and have the configuration there, or you just specify it manually using the command line or the web interface. There, I had some idea that we might want to do that in a future version, have that be a bit more flexible, but I can't promise you when that will happen or if that even will happen.
Okay. There's another question around networking. It says, does OpenShift, Red Hat, or Linbit prefer any specific third-party networking projects to implement Kubernetes networking model when there are many choices? Any suggestions for evaluating the many choices that are listed on the Kubernetes.io site?
Maybe Taylor, that's more for you, but from the Linbit side, any of the Kubernetes networks seems to work. We are testing with OpenShift. I think it's currently OVN, and that works fine. We also have other Kubernetes cluster where we are running Calico, and it also works fine.
Yeah, I would say, I mean, our defaults are going to be SDN and OVN, and then Calico is really prevalent, but outside of SDN and OVN, we're pretty agnostic. We don't have like a vocal preference on a specific one.
Okay. That answers all the questions. And it leaves us with 9 minutes before the next webinar. So guess if there's no other questions, we can go ahead. We did have one pop in. When creating snapshots of the volumes, is the pod somehow informed of the clear cache?
No, currently that doesn't happen because so for the when we create a snapshot, the CSI controller gets informed that we want to create a snapshot. That informs the Linstor controller that there's a snapshot, and that then creates the snapshot on the satellites. But those satellites have no information about any mounted volumes on the device. So it just freezes I/O so that you have a consistent snapshot image, but it might not be synced with all the latest changes if you're running from some kind of file system cache or so on top of that. If that is something we can fix, I'll have to think about that. I'm not sure if that's easily possible.
Okay. And that is the last question. So with that being said, thank you for your time, Moritz and Taylor. And we will see anybody else at the next webinar here in about 8 minutes.